really high up there, then the energy difference from here to there is going to be a lot. You're going to be producing a lot there's a lot of energy difference. You're going to be producing a lot of heat, a lot of energy. And this is the difference between using methane and oxygen and an oxyacetylene torch. An oxyacetylene torch, it burns acetylene. You have the oxygen and you have acetylene. It burns the acetylene. This is used to weld metal. So this can even melt metal. So in that case, the energy difference is way higher for the acetylene and the product. The products, by the way, are always carbon dioxide and water. So the only question is, what are your reactants? Is it methane, or is it possibly acetylene here, where you have your activation energy and you zip all the way down to produce a lot of energy? These heats that it produces, that it releases, they're heats of combustion, and every reaction can have a different heat of combustion. Let's also talk about the activation energy. You have a match. Imagine a match. Now, a match will burn in the oxygen. But if you just hold a match in the air where there's plenty of oxygen, it's not going to light. You need some kind of activation energy. So the friction of the matchstick will produce enough heat to get that activation energy, and then the wood of your matchstick will be able to burn. It'll react with the oxygen, produce the carbon dioxide and water, and release enough heat. That other heat will enable the rest of the wood to burn until your matchstick is gone. You have to have the right amount of energy. A tiny amount of energy wouldn't do it. You have to be high enough. That's called the ignition temperature if it's heat that's causing this activation energy. At a crime scene, what actually made the thing burn might not be a match or anything else. It might be some exposed wires that electricity goes through. Even sunlight, magnified sunlight, you can focus it on paper or something else that might have caused the fire. Might have caused the initial activation energy, after which everything burned. Well, again, the difference between the initial fuel and the oxygen and the products, the energy difference added more activation energy. But the initial burning, the initial activation energy, we have to know what it is. Sometimes it's clearly arson, because we see, let's say, a lighter was used, but sometimes you might not see it. It might be exposed wires or magnified sunlight, or there are various things that can cause fires that can produce this initial activation energy. Even bacterial action can be used to eventually achieve the activation energy. But in any event, the arson investigator has to check for all other possibilities for what caused the activation energy. It might not have been a person doing it. It's important to know about the rate of the reaction. Now, oxidation rust, iron reacts with oxygen, it'll form rust, but that is slow. But burning or even explosions, those are very fast. So we have to know about the rate of the reaction. When the fuel is in the state of a gas, meaning the fuel is a gas, like for example the methane, the CH4, the natural gas is a gas, and it's mixed with oxygen, it burns much faster. That's why our gas ranges that we cook food on, they're very efficient in getting this reaction to work and producing the heat, because it's a form of a gas. It mixes very well with the oxygen, so it's easy to burn. It's also easy to control, because when you turn off the gas, the fire will go out. So it's very easy to control. That's not the reason we use it. Anyway, liquids don't work that well. But you might be wondering, what about gasoline? That burns well. The fact is, it's not actually the liquid of the gasoline that burns. The gasoline is very volatile. That means it evaporates very quickly, and right above the surface of the gasoline, there's a lot of gasoline in the air. That gas is what burns. So I wouldn't advise this, but if you take a match and you throw it really hard into gasoline, the match will pass through that vapor, that gasoline vapor, before it can ignite, and the match will get into the gasoline, into the liquid gasoline, and it'll actually go out, because the liquid gasoline won't burn. It's the gas above it. So if you're quick enough with this, you can actually throw a match into a can of gasoline, and it'll actually go out. Again, not advisable, but at least in theory, this actually works. You can put out a match when it's immersed in gasoline, but it will ignite everything when it's in the gas layer, the evaporated gas layer of gasoline above the liquid layer, above the liquid surface. Oh, it's also true that solids can also turn to gas at higher temperatures. It's often called pyrolysis. It can also be called sublimation. So the thing is that solids don't have to turn into their gaseous state before they actually react. Solids, as solids, they can actually ignite and produce a fire. Now, what often happens in the case where we have a flame, believe it or not, the heat of, let's say, the charcoal. The heat of the charcoal, it's a charcoal flame. There's a flame on charcoal. The heat of the flame will actually cause the solid to evaporate a bit and produce a little bit of a gas above itself. That gas ignites in the form of a flame. It's also true that solids can react even without the flame, if you like, a glowing charcoal. In that case, what's reacting is the charcoal itself, but not the gas above it. But very often when you see a solid burning, let's say a match, it's actually the gas form of because of the heat, the gas form of the solid just above the solid surface that's really burning. But the solid itself is not burning. But again, some of the solids themselves can react, can burn. It's generally true that when you add heat, the reaction goes faster. So this is important because if you have a room where there's a fire in there, the more the fire, the more the heat in the room, and the faster the fire will burn. So this is important. The reason why has to do with the fact that there's more heat. There's more fuel in contact or able to absorb the activation energy, and therefore it will react, and therefore more will burn, and it'll burn faster. Now, it's not always true that adding heat will make reactions go faster, but for our burning situation, it's true. The fact is, reaction rates is a very complicated subject. It's called chemical kinetics, and there's a lot of information and a lot of theory behind it. We're only dealing with a very generalized theory of why some reactions go faster than others. There are three things that a fire needs. Fuel. It needs fuel. Without fuel, it goes out. The wood turns to ash, no more fuel, fire goes out. You need oxygen. If you let's say have a match and you put it in a cup and you cover the cup, eventually oxygen will be all burned up, no more oxygen, the fire will go out. That's you can smother a fire that way. For example, you take a match, put it on a table, you cover it with a glass. Eventually, the oxygen inside the glass will be burned up and no longer available for the burning, and the fire will go out, and you'll see it. And you also need heat. Remember, that had to do with the activation energy. Without heat, if you can somehow siphon off the heat, the fire will go out. This, by the way, is one of the reasons why putting water on a fire works. Number one, the water carries away the heat. Number two, it covers the fuel so that oxygen doesn't get to it. So this is why water puts out fire, in case you needed a complicated explanation as to why. In any event, you need fuel, oxygen, and heat for fires to go on and to continue. You need the fuel because once there's no more fuel, you have no more reactant, you don't have a fire anymore. The availability of the oxygen. So again, oxygen is a reactant. You lose the reactant, you'll no longer get the product. This is very important because we have to have both fuel and oxygen. When things burn in air, let's say natural gas in air, we have to know, in order for it to happen, the mixture has to be correct. You can't have too much fuel, because if you have too much fuel, let's say too much fuel over here, then you don't have that much oxygen. If there's no oxygen, it won't be able to burn. You need oxygen too. If you have too much oxygen, meaning very little fuel in the air, well, again, not much will burn because you need the fuel. So you need a correct mixture of both fuel and oxygen in the air in order for it to work.